Hello again, this is the Pencrest High School AP Physics 1 video series. This is video 8C, one-dimensional wave behavior. So we have several one-dimensional wave behaviors that are of interest. A one-dimensional medium is something like a rope or a stretched spring, strings on a stringed instrument. The best example is the big long spring we used in the hallway. The first behavior we're going to look at is reflection. Wave reflection is what happens when the wave reaches the end of the medium or runs into a barrier that it can't penetrate. There are two kinds of wave reflection we'll look at, free end reflection and fixed end reflection. That has to do with whether the end of the medium is held in place or not. We also have what's called refraction. Wave refraction is when a series of waves go from one medium into another. We think of two long springs attached at the ends. The springs have different tensions and masses, and therefore they have different wave speeds. When the wave speed changes, that's the definition of wave refraction. When it goes into a new medium, the wave speed changes and the characteristics of the wave will also change. We have what's called partial reflection and partial refraction. This is a realistic wave behavior. That's what really happens when waves go from one medium into another. Some of the wave energy is refracted into the new medium, and some of the wave energy is reflected off the boundary back into the old medium. So we'll see that after we look at the first two. And the last one is called interference. This is another major characteristic in which waves differ from objects. Waves can occupy the same place at the same time. Objects can't. When waves collide with each other, they superimpose themselves. That is, they effectively they add up. There are two kinds of wave interference, constructive and destructive. Again, this is a major difference between waves and objects. The principle of superposition is what says that waves can occupy the same place at the same time. Now, first we'll look in some detail at reflection. First, we have a free end reflection. The end of the medium here is free to move. When you look at these static images, read the sequence from left to right. The end of the medium here is shown as a ring that can sort of slide up and down this pole here. This wave crest here is moving from left to right towards the end of the medium. It's going to hit the end of the medium and lift the end of the medium up and then back down again. And the wave crest reflects off this free end such that it's just moving in the opposite direction. Nothing about this wave changes other than the direction of its velocity. So free end reflection, it reflects off the end and just goes back in the opposite direction. Same amplitude, same wavelength, same speed, opposite direction, but same magnitude of wave velocity. Now, when we have a fixed end reflection, the end of the medium is fixed, that it is not free to move. The sequence again reads left to right. First panel shows this wave crest or wave pulse approaching the barrier. When it bounces off the barrier, we see that the wave crest has been inverted and it becomes a trough. So a crest, when it reflects off a fixed end, becomes a trough. If a trough reflects off a fixed end, it becomes a crest. Again, the wavelength doesn't change, frequency and period don't change. The amplitude flips, but it's the same amplitude on the other side of the rest position. Now we have wave refraction. This is when a series of waves moves into a new medium. A new medium is defined as one in which the wave velocity changes, either by speeding up or slowing down. In the event that we have a faster medium into a slower medium, when the wave speed decreases, the wavelength decreases accordingly. So the frequency of a given wave, once it's generated, regardless of any changes to its wave speed, the frequency remains constant. So in order for the frequency to remain constant, when the wave speed decreases, the wavelength must also decrease. There is also an amplitude decrease. It's harder for the waves to move the slower medium. You can think of the slower medium as being a heavier spring or a heavier rope. So it's harder for it to move, and the resulting amplitude is smaller. When the reverse happens, when we go from slow to fast, where the wave speed increases, and the wavelength must also increase. Again, the frequency remains constant, so when the velocity goes up, the wavelength must also go up. Notice that the amplitude in the fast medium increases because the wave moves the faster medium more easily. It's a lighter spring, so it moves with a greater displacement, a greater amplitude when the waves move into the fast medium. Now, when we deal with partial reflection and partial refraction, again, this is a more realistic behavior. Some of the wave energy gets refracted and goes into the new medium, and some of the wave energy is reflected back into the old medium. So first we'll look at from slow to fast. Here's a wave pulse traveling along the slow medium. This is the boundary between the slow and the fast, so the wave speed will change when it passes right here. And what we see is that some of the energy gets reflected. Here's the reflected wave pulse. And some of the energy gets refracted. Here's the refracted wave pulse. The energy that is reflected behaves like a free end reflection, so it doesn't flip over. So the crest reflects as a crest. And then here's the refracted wave pulse with a bigger amplitude, longer wavelength. Notice that the amplitude of the reflected pulse has decreased because the energy gets split up. So some of the energy goes this way, some of the energy goes this way. When we look at what happens to each of the wave quantities, on the left here you have the reflected wave pulse. The velocity is the same but in the opposite direction. The amplitude decreases, frequency and wavelength are the same. In the refracted wave pulse in the new medium, we have an increased velocity. That's the slow to fast. So the velocity increases, the amplitude increases, the frequency is the same, and of course because velocity increases, the wavelength must also increase. When we look at the reverse, we have fast to slow medium. Again, here's the boundary. Here's my wave pulse on the way in. When it crosses the boundary, some of the energy is reflected, some of the energy is refracted. We see that the reflected wave pulse behaves like a fixed end reflection because the slow medium is harder to move. So it behaves like a fixed end reflection and flips over. So the incident wave crest reflects as a trough. It refracts as a wave crest. Notice that the wave quantities, again, the reflected pulse, it's the same. Velocity is the same, but in the opposite direction. The amplitude decreases and inverts, so crest becomes trough. Frequency and wavelength are the same. On the refracted side, the velocity must decrease. That's the change from fast to slow. The amplitude will decrease. The frequency is the same, and the wavelength will decrease according to V equals F times lambda. Okay, now interference, once again. Critical difference between objects and waves. Waves can occupy the same place in the medium at the same time. There are two basic types of interference. We have constructive and destructive interference. First, we'll look at constructive. We have wave crests A and B approaching each other in the same medium. A is moving left to right, B is moving right to left. When they run into each other, okay, they will superimpose, like we said before. The principle of superposition says that A and B will sit on top of each other, and their amplitudes will add such that the amplitude of the resulting wave crest is A plus B. So in effect, we get a bigger wave. We get a bigger wave crest than either A or B. That's why it's called constructive interference. The key thing about waves is that when they interfere, they only superimpose while they're on top of each other, and they continue moving. B continues moving right to left, A continues moving left to right, as if nothing happened. So they don't trade energy, or they share energy briefly here, but they just keep going as if the interaction never happened. So they pass right through each other, and they continue moving in their original directions. Again, this is constructive interference because it constructs a wave that is bigger than either of the two that are added. Now, destructive interference is the opposite. We have a wave crest A approaching a wave trough. The crest is moving left to right. The trough B is moving right to left. When they collide, if they happen to have the same amplitudes, they will cancel each other out. So temporarily, when A sits on top of B, we have effectively no displacement in the medium at all. Again, they continue moving past the interaction like nothing happened. So here's B continuing to the left, here's A continuing to the right, as if the interaction never happened. This again is called destructive interference because the resulting amplitude is smaller than either of the two waves that were added to create A plus B. Okay, so those are our one-dimensional wave behaviors. We'll look at a particular application of interference and fixed end reflection next up when we look at standing wave patterns and the harmonic series. Until then, enjoy, and I'll see you again soon.